these 4 points we have in chapter 2. So we start talking about pure substances. What are the substances that we can classify as pure? What are the phases that we have for these different substances? And what is the name of the phase change processes we have? Then we need to describe the properties between these phases. So we explain the phase diagrams. And we said we can have 2-dimensional diagrams. We can have 3-dimensional diagrams. We showed like sample of each one of them. Then we start to know, okay, what if we need to know the properties that we have? So we started with explaining the steam tables last lecture. So these are tables for steam, only for steam, having all the properties you need for steam. We have 4 tables, 2 of them for saturated steam or saturated liquid based on the temperature or pressure given. The other one is superheated vapor, the last one for compressed liquid. Clear? Okay. What we need to do today we will start the thermodynamic models of physical properties, the last point we have in this chapter. This can take 2 lectures for us. And today we need to describe new forms of energy. So far we said we have kinetic, internal, potential, we have heat wall, but we have other different types of energy. Okay, one of them is the enthalpy. Okay, so enthalpy, this is one of the forms of energy that we will use a lot in thermodynamics. So how we can define enthalpy, or how we can calculate enthalpy. For steam tables, if you remember, there were some columns for enthalpy values. So sometimes for steam, for example, you can get these values just from the steam tables. But what is meant by enthalpy? Even how can we calculate it if we don't have tables? Are there any equations we can use to calculate enthalpy? And by the way, similar to internal energy. Internal energy in chapter 1, this was the only form that we didn't define any equation for its calculation. We just said this sort of energy comes from the molecular interactions, maybe the movement of the molecules. But last lecture, when we showed the steam tables, this was our first source that we know how we can get values for this internal energy. So what if we don't have water, for example? We don't have tables available for the substance we are dealing. How we can calculate the internal energy? So this will be the answer that we have to find. This is the question that we have to answer this lecture. So enthalpy, again, this is a state property. So state property means it depends on the path of the process, or only depend on the initial and final states? Initial and final states. It doesn't care about the path properties, or this only a heat and work. So this is a state property. And this form is also used to represent or quantify the amount of energy your system has. Again, it's similar to internal energy, cannot be measured, which means we need to quantify or estimate of value relative to a reference. And again, this means you can have negative enthalpy values, okay, similar to internal energy. So internal energy and enthalpy, they are similar in terms of we can't measure their absolute value, we just measure the difference in the internal energy, the difference in the enthalpy, so we need a reference. So based on your reference selection, you can see negative enthalpy values, similar to internal energy. Okay. How we can find, or how can we calculate enthalpy? So when we start to analyze systems, especially for open systems, in open systems, we have static form of energy, which is internal energy. In open systems, you have fluid moving, right? You have inlet, you have outlet. So this is why you have flow work. So always when you analyze any open system, you will have these 2 terms are repeating in all the mathematical derivations. Internal energy, flow work. Internal energy, this is a form of static energy. Flow work, this is a form of the dynamic energy, the work that is associated with open systems. So we said we will combine these 2 properties because they are repeating in all the mathematical equations, and together we will combine them in a new property, and this property we will call it enthalpy. So enthalpy is basically the summation of internal energy plus flow work. Summation of internal energy as one form of the static energy forms, and flow work as one of the forms of the dynamic energy forms. Okay, but again, this one is extensive property, PV is extensive property, and we don't prefer to use extensive properties in our calculations, so we need to convert this formula to intensive. So this is why we can divide this equation by mass, and we have it specific enthalpy equal specific internal energy plus P specific volume, or we can divide it by mole, so we have molar enthalpy equal molar internal energy plus P molar volume. So this is the originates. Enthalpy is a property, quantify energy related to internal energy, and enthalpy is summation of internal energy plus flow work. This is why when you are analyzing a closed system, you will not see enthalpy in the equations. Because closed system, we don't have mass in or mass out, so we don't have flow work. So the PV term does not exist. So only internal energy term will appear. But when you analyze open system, we have internal energy, we have PV, so just try to simplify the equation, combine these two terms together and call them enthalpy. Clear? Question so far? Okay. So to answer this question, how we can find enthalpy, how we can find internal energy? So simply, if you have a steam, use the steam tables. But if you have different substances, or if you don't have any tables or any data available to find or get this value, then we should calculate them. And in order to calculate enthalpy or internal energy, we should start with understanding what is meant by heat capacity. And why we have two expressions for heat capacity. We have heat capacity, we can term it as CP, and we have heat capacity CV. Anyone know what is meant by heat capacity? Anyone hear this one before? Yeah.
The amount of heat it takes to heat a substance by 1 degree Celsius.
Exactly. So the thing is, heat capacity, this is the amount of energy that you need to add to any substance just to increase the temperature of this substance by 1 degree Celsius. Okay? Why this one is important, or why this one is related to internal energy and enthalpy? As we said, one of the parameters that affecting internal energy is temperature. And temperature is a fraction of the energy. So here we can relate energy to temperature. So this is why heat capacity start to be introduced as one of the properties that we can use to calculate internal energy or enthalpy. The definition, exactly as you said, heat capacity is the amount of energy that is required to raise the temperature of any substance by 1 degree. Okay. So now let's bring a substance, fixed mass of a substance, and apply or provide the substance with energy to increase the temperature. We have two experiments are being done. So the first one will bring 1 kilogram of substance, and in the second container we bring also 1 kilogram, same amount. And in the first experiment, we ensure that the volume is constant. Okay, so we have a rigid wall container. There is no change in the volume that we have of this container. So we put 1 kilogram of a substance and we start to apply energy or heat this substance we have in this tank. And then we found in order to increase the temperature by 1 degree Celsius, then the amount of heat needed is 3.12. So we need to add 3.12 kilojoule to 1 kilogram of this substance to increase its temperature by 1 degree Celsius. Same substance, same amount, but this time we make the pressure constant. And we start to heat the substance. And what we found? We found that we need to heat it or add amount of energy 5.19 kilojoule for the same amount of substance to increase its temperature by 1 degree Celsius. So here in these two examples, we have just one substance, same amount, everything is almost the same. But at one condition, it needs certain amount of energy, which is 3.12. At the other conditions, to achieve the same goal, to increase the temperature with the same increment, it needs other amount of energy. And the only difference in this one is how you perform your process. So this is why we have two forms of heat capacity. One describes the amount of heat this substance has to increase its temperature if the process operates at constant volume. And the other one, the amount of energy needed if this temperature change will occur at constant pressure. So again, this is why here we have these two types of energy. We have this one, CP, we have this one, CV. So this one represents heat capacity. The subscript B, it means this process occurs at constant pressure. So this is the heat capacity, energy needed by any substance to raise the temperature if you will heat it at constant pressure. CV, the amount of energy needed to raise the substance by 1 degree Celsius if your process will occur at constant volume. So far is clear? Clear? Okay. So, so basically what we have here, if we have like this x-axis, we make it temperature and we need to change the temperature. This is the first experiment that we have at constant volume. This is the second experiment that we have at constant pressure. And we just see the amount of heat we are adding to this system and the temperature change, and we will have this black line. We have this line that describes the relationship between the amount of energy added and the temperature that you have. At any time you can see the slope at this temperature, and this slope will be equivalent to CV. And any temperature you can just at any one and get here, draw parallel to the curve, and this slope will be CP. So here both of the y-axis here represent the amount of energy added. Here we have also the y-axis represent the amount of energy added. But here we have this amount energy represent change in the internal energy. So internal energy, this one is related to CV, and here we have the amount of energy, delta H, which is related to CP. So again, from where this comes from? Here in the system we have constant volume, we have internal energy, but we don't have flow work. There is no like PV, there is no movement in the piston or in the volume. So the amount of energy or the temperature change will only reflected on the delta U. There is no PV. So the amount of energy here we had, this is reflected by delta U. But here in constant pressure, we have the movement that can happen for this piston. So here we have internal energy, here we have PV, and again, both of them together can be combined to represent enthalpy. So this is why we have CP, or the experiment that is conducted at constant pressure. We have PV term, we have internal energy, so this is why we can have enthalpy. So this is why after we define this heat capacity, so I said we have two of them. One of them represent heat capacity at constant pressure, one of them heat capacity at constant volume. Then we can use the CV to calculate the internal energy, and we can calculate CP, this one, to find an equation to calculate enthalpy. So let's summarize all what we have. So we start with defining enthalpy. Enthalpy, summation of internal energy plus flow work plus PV. We can find it from steam tables. If you have a steam, go to the steam tables and find the value of enthalpy, find the value of internal energy. So what if we don't have tables? What if we don't have a substance that we don't have like available data for enthalpy and internal energy? So in this case, we need to calculate them. So how we can calculate enthalpy? How can we calculate internal energy? Again, we have an equation, H is U plus PV. But if both of them is missing, so we can't use this equation. We need other equations that we can calculate H or we can calculate U. Then we define the heat capacity, the amount of energy that any substance has to increase its temperature by 1 degree Celsius. Then we did experiments and we find we have two definitions for the heat capacity based on how the process is performed. We have heat capacity, certain amount of energy this substance needs if the process or the heat added for the process operates at constant volume, or if the process is conducting at constant pressure. If the process is conducted at constant volume, so the heat capacity will be called CV. And this will be the property that we will use to find an equation to calculate internal energy. And heat capacity at constant pressure is CP, and this is the property we will use to develop an equation to calculate enthalpy. Clear? Questions? Okay. So again, these are the two curves we have. Enthalpy with temperature, the slope is CP, internal energy with temperature. So if we just repeat the plot, and we can say if we put CV on the y-axis, temperature on the x-axis, and we calculate the area under this curve we have, so we have du CV dt, then we can say the change in the internal energy is nothing but this area, which is the delta U, nothing but CV dt. And also, if we have this figure and just repeated it in different way, that we have Cp on the y-axis, temperature on the x-axis, to the area under this curve, which is delta H, this one can be calculated by integration of Cp dt. So these are the two equations we have. So if you have Cv, then you can say Cv is nothing but the change we have in internal energy with respect to temperature at constant volume, and then can be done specific or can be done molar based on the Cv units. Cv units can be described as per mass or can be described as per mole. And Cp also is nothing but the value of Cp is the change we have in the enthalpy with respect to temperature if the process operates at constant pressure. Clear? Any questions so far? Okay. So now these are the equations that we need, or we should use in order to find the internal energy or enthalpy. So just this one, we use it to calculate internal energy. This one, we use it to calculate enthalpy. Okay? So how can we use these substances if we have liquid or solid or gases? Solids and liquids have the same classification, the same category, but gases have something different. Or in other words, what can we say that, or do we have any cases in which internal energy and enthalpy can have the same value or they can be different? So this one, we will start looking if we have liquid, if we have solid, what will be the case we have? We know that for liquids, for solids, the system is less sensitive for any changes in temperature and pressures. Liquids or solids are classified as incompressible. Their density, their volume are not changed with temperature and pressure. So this is why we can say volume of liquid, volume of solid is almost constant. So if we need to find du, which is d CVT, CV will be constant, it's not affected by this one, so we have du as CV dt. And again, if we got to this one here, if you remember when we start to explain the kinetic and potential energy and how the kinetic and potential energy values compared with internal energy, so we said internal energy value is very huge compared to kinetic and potential. You remember this from chapter 1? So this will be the same here. I have enthalpy, it's internal energy plus PV. Okay. This internal energy value is very huge. For liquids and solids, this value will be very small compared to internal energy. So we can neglect this one, and we can say for liquids and solids, the value of enthalpy can be almost equivalent with the value of internal energy. Or in other words, we can say the value of Cp equals the value of Cv for liquids and solids. So this is the first case. We have an equation to calculate internal energy. Change in internal energy is Cv dt. Change in enthalpy is Cp dt. If you are dealing with solid, if you are dealing with liquid, their volume is less sensitive to pressure and temperature changes. Their volume is very small compared to the internal energy values. So the term PV can be neglected in the calculations, and we can assume that enthalpy value will be equal to internal energy value for solids and liquids. Or in other words, Cp and Cv values will be the same for liquids and solids. This one is clear? So if you have any example, if you have any solid, if you have any liquid, I ask you to calculate the internal energy, then you can calculate it. If then I ask you to calculate the enthalpy, don't make any further calculations. The same internal energy value is the same as enthalpy value for solids and liquids. Clear? Okay. Let's take this example. So this example says we have liquids. When you see this word, when you hear it, liquid means we have the value of Cp equal the value of Cv, which implies that the value of internal energy equals the value of enthalpy. Just this should come in your mind when you see a liquid or when you see a solid. Okay. Ezra, clear? Okay. We have Cv is 2.15 joule per gram Kelvin. What is the change in the specific internal energy when this liquid is heated from 295 to 300 Kelvin? Okay. So we have liquid at 295, we need to increase its temperature to 300 Kelvin. We have the heat capacity for this one, so we need to calculate the change we have in the internal energy. So this substance here we have, this substance we have liquid. So what this means, we have du as Cv dt, or we have du as Cv dt. You can find the specific internal energy or molar internal energy. So based on the value, the Cv given value here, the Cv is 2.15 joule per kilogram Kelvin. So the value of Cv we have here, this one is per what? Per kilogram. So if you substitute Cv in the equation, which one you will calculate? Will you calculate the specific internal energy or will you calculate the molar internal energy? The specific. Okay, so make sure that the units are consistent. So this one, or based on the value we have, this one doesn't match with the units. Okay, so this one can't be used, and this will be the correct equation. So how I know this is the correct equation? Just go to Cv value expressed per mass. So if you put it, you will calculate the specific internal energy. And this is what you need to find at the end. And the question he said, calculate this specific internal energy. Okay. So we have this du as Cv dt, then we can say by integration, then delta U is integration of Cv dt from initial temperature to final temperature. The value of Cv, based on the given we have in the problem, is it constant or function of temperature? It's constant. Since it's constant, we can take it out of the integration. So this will be Cv integration of dt from T1 to T2. So this one will be Cv T2 minus T1. So again, let's write the equation. So the change we have in this specific internal energy will be Cv T2 minus T1. Everything is given. So we have T.15 T2 minus T1. Just we need to check the units. So this one, the units we have is joule per gram Kelvin. This is gram, not kilogram. The temperature we have here is Kelvin. So if you just put in the units in this example, you will see that this Kelvin will be cancelled with this Kelvin. And at the end, you substitute the numbers. So what you will have, the change in the internal energy will be 10.75 joule per gram. And this is what we need to find. Clear? So if I ask you what will be the change in the enthalpy, it will be the same value. Okay, so we can put it in a note here. So since we have liquid, so this means the change in a specific internal energy equal the change we have in specific enthalpy, which is 9.7 joule per gram. So this is just in case if I ask you what will be the value of the enthalpy you have. Any questions? Okay. So now, one of the things that you can check your solution, so the delta U, the change in the internal energy we have here was positive. So this one, this value was positive. So do you think, is this consistent with the process? So the process here, what is happening? You are increasing the temperature of your substance. So by increasing the temperature, so do you think the internal energy will increase or decrease? It will increase. You are increasing temperature, increase collisions between the molecules, so it makes sense that the internal energy decreases. For any case, if you have like negative values, which doesn't match the information we have in the problem, then you need just to check any term that you may like replace them. Clear? Okay. Now let's go to the other side. If we have gas, okay, how can we calculate internal energy? How can we calculate enthalpy from CV and CP equations if we have gases? Gases, we have two types of gases. We have ideal gases, we have real gases, right? So what is the features of ideal gas? Ideal gas, we have normal intermolecular forces. There's no forces between the molecules. The volume of this gas or the molecules are neglected compared to the whole volume of the gas. And then even if you have collisions, these collisions are elastic. So ideal gases, molecular volume neglected, molecular collisions also neglected. Okay. So for ideal gas, we have an equation of a state was derived to describe the PVT relation for ideal gas. Equation of a state, this is any equation that contains pressure, volume, temperature. Okay, have these three ones. So scientists, they did a lot of experiments and they said if we have ideal gas, so for this ideal gas we can say PV equal nRT. This looks familiar to you? Okay. If we divide both sides by n number of moles, so we have P molar volume equal RT. R, this is the ideal gas constants, and we have list of the values of R here. Okay. So make sure that you can use any value of R that's consistent with your problem. Okay. This is one of the mistakes we see in the exams. Just what are the units you have in the problem, then which of these are that will be used. We have different values of R, but let's say these are the most common values that you will use in the problems. Okay, clear? The value of R, if you notice in all of them, is described per mole. But again, we have R values that can be described for per mass. So even R value can be expressed per mass, not per mole. But this one will be different from one gas to another. So this is why we are using the R value that is per mole, but this is a universal value. Okay, but let's say if you have air, for example, so this is the value of R for air if you want to express it per mass. If you have nitrogen, so R will be different for nitrogen. So each substance has its own or specific ideal gas constant if you want to express this ideal gas constant per mole. And again, if you will use this equation, so the most important thing when you use the temperature, temperature must be the absolute. It should be in Kelvin, must be in Rankine, any one of them. It can't be in Celsius, it can't be in Fahrenheit. Okay? So let's take an example just to remind you how to use this equation. Let's say we have tank. This tank contains compressed oxygen at 20 degrees Celsius at 1000 kilopascal. The volume of the tank is this value. Use ideal gas equation. Calculate the mass of oxygen inside the tank. Okay, so how can we solve this one? Again, this is the problem we have. So you can solve it like we have several ways we can use it to solve this example. So let's start with solution one. So we know that the ideal gas equation is PV equal N RT. Here required is to calculate the mass, right? Do you see mass in this equation? No. You have pressure, volume, moles, ideal gas constant, temperature. There is no mass. But one of them can be converted or related to mass, which is number of moles. So we know that number of moles is mass divided by molecular weight, right? So the equation here you have is pressure, volume times molecular weight. This equal to mRT. And then start to put the numbers we have. So we have pressure. Pressure is given as 1000 kilopascal. Kilopascal, this is how we express pressure in SI system? No? So what is the pressure units in SI system? What is the pressure? PSI. You agree?
Oh wait, SI system. Wait, no, PSI is in here.
PSI is pound force per inch square. It's American system.
Yeah.
Atmosphere. We repeated this same question last week,
Yeah, it's so fast.
and you're repeating the same mistakes. Only one of you said the correct one, which is
I didn't say it.
really? Okay. Someone was sitting here said, what is the pressure units? Pascal. So the pressure in SI system is Pascal. Remember this. Okay. So this one will be thousands times 10 to the power 3 Pascal. Okay. Chapter 1, you have some slides explain the units of work, the units of energy, the units of pressure, okay, in the different system of units. So make sure that you have, see this one. Volume is 0.12 meter cube. Do we need to convert this one, or this one is consistent with the units? It's just consistent, meter cube SI system. Okay, the molecular weights of oxygen. This one is 16 times 2, so this one is 32. Okay, usually we don't put the units of the molecular weight, it have mass or per mole, right? So even Dr. Lux usually tells you we don't put the units because it's a gram per mole or kilogram per kilomole, so we just put the number. Mass, this is what we need to calculate. Or this is the ideal gas constant. Now we have everything in the SI system. So what is the value of R in the SI system? Again, see the previous slide. You will see 4 values. The first one of them is the one for the SI system, 8.314 joule per mole Kelvin. And then we have the temperature. Temperature here is 20 degrees Celsius. Should we put 20 degrees Celsius? No, we should convert it to Kelvin. So this one will be 20 plus 273. So this one 293 Kelvin. Almost we have everything. Put the numbers in the equation, then you can calculate mass. So the mass of oxygen we have here will be 1576.35. Clear? So do you think we finished the solution? When you put a number, don't forget to put what? The units. So what will be the units of this mass?
That's grams.
Usually the mass in the SI system is kilogram, right? But here we have, who said gram?
Gram.
You said gram. So if all the units we have, we convert it to SI system, right? So do you think the number we have here is in gram or kilogram?
Gram.
What?
It's grams.
It's in gram. Why in gram? I put both of them. Here we have gram, here we have kilogram. So which one is correct?
You should put it in kilograms.
Kilograms.
I say great.
Grams.
We're going to get it in grams because we have the molecular weight as 32 grams per mole.
So it would be in grams, but we can turn it into kilograms.
But the molecular weight is 32 grams per mole, and also 32 kilogram per kilomole. 32 pound mass per pound mole. The molecular weight is the same for all units. So this is not the reference.
We did 8.314, which is joules over mole per thousand.
Yes. Thing here, which was you were close to it, not the units of the molecular weight, but the units of R. R is 3.14, right? 3.14 joule. This is SI system. This is why we convert all the numbers to SI system to match joule. Kilogram, this match what we have here. Then we have what? Mole. Just because the value of R that you selected is expressed by mole, not kilomole. So this is why the correct number will be gram. So this is right, this is wrong. And again, this comes from this one here. If you have value of R, for example, which is a number joule per kilomole Kelvin, so now you have kilomole, so the value that you calculated automatically will be kilogram. Clear? Questions? Okay. So this is the value we have here. So just we can just divide by 1,000. So this will be 1.576 kilogram, and this is what we need to find at the end. Or we have another solution. So someone can say we can do the following. We can say we have PV instead of nRT is mRT, and then look for value of R. So we need R value for oxygen expressed per mass or by mass. So for oxygen, the value of R per mass is 259.8 joule per kilogram Kelvin. So there is a value of R expressed by mass for every substance. This is a constant number for every substance. So you can use it directly. So you can put the numbers again, then you can say 1000 kilopascal times 10 to the power 3 to convert it to Pascal, times volume 0.12 meter cube equal M times R 259.8 times 20 plus 273. Calculate the numbers, then you will find the value of mass, the same number 1.576 kilogram, and that's it. Any one of them is correct. Questions? Okay, let's take one more example. Last thing we have today. One more example says we have 3.5 kilogram per second of air at 100 kilopascal. Again, 100 kilopascal, this is not SI system. So how we can convert it to Pascal, to SI? So this one will be 100 times 10 to the power 3 Pascal. At 25 degrees Celsius, we need to convert it to Kelvin. Is to be inducted into an air compressor. The air will exit the compressor at 800 kilopascal, 300 degrees Celsius with the same mass flow rate. Use ideal gas law, determine the volumetric flow rate at the entrance, this is requirement number 1, and at the exit, this is requirement number 2. So here we have two requirements. We need to calculate the volumetric flow rates, one time at the inlet, one time at the outlet. And he said clearly use the ideal gas law. So what we can do in this one, again we have ideal gas law. we have PV equal nRT. Right? Here in the problem, we have mass flow rate given. The requirement is volumetric flow rate. So volumetric flow rate, this is volume divided by what? Time. Rate means anything divided by time. So this one will be PV over time equal nRT over time. So this will be pressure times the volumetric flow rates equal molar flow rate or T. And this is the volumetric flow rate. This is what we need to calculate. So you make the calculations twice, one time at the inlet, one time at the outlet. So let's go to the inlet. So the pressure at the inlet is 100 times 10 to the power 3 Pascal. The volumetric flow rate at the inlet, this is what I need to calculate. The ideal gas constant let's put it now. So we have the temperature at the inlet. So this one is 25 plus 273. So this one 298 Kelvin. Then we need to find the okay, let's put it this way. So we have this equation, we can put it this way. Here we have the molar flow rate. We have no idea what is the molar flow rate, but we have mass flow rate given. So since mass flow rate given, we can, instead of using the equation at this side, we can say PV dot equal M dot RT. And this one here, this R will be by mole. But here, if you will use this form, this should be by mass. Or you can just convert mass flow rate to molar flow rate by dividing on the molecular weight. So you can do any of them. So the mass flow rate, this one is given 3.5 kilogram per second, and this is SI system, we need to convert it. And the value of R for air in the mass units is 287 joule per kilogram Kelvin. Again, go back to the slides that contain R values, you will find this number. So now we have everything. We have pressure, we have temperature, we have mass flow rate, we have R, everything is in this equation. So substitute in the equation, then you will find the volumetric flow rate at the inlet. So this one will be 2.99 meter cube per second, and this will be the first requirement. Clear? And we can go to the outlet. Substitute in the same equation with the conditions at the outlet. So what are the conditions at the outlet? We have the pressure is 800 times 10 to the power 3 Pascal. Temperature is 300 degrees Celsius plus 273, so this will be 573 Kelvin. Mass flow rate, this is the same, 3.5 kilogram per second. Or will be the same, we have the same substance. Substitute in the equation, then the volumetric flow rate at the outlet, so this one will be 0.72 meter cube per second, and this is the second requirement. Clear? Any questions? Okay.